In this video, let us introduce the theory of the substitution method. It is usually introduced as an algebraic procedure with Leibniz's brilliant dx notation. It is convenient notation for all of us, but not sufficient to justify the method. For beginning students, distinguishing the differential form dx from the quantity delta x will take a long foundational work. So we formulate the method as a theorem, and do a bit better than treating the method as if a proof. Let us call this substitution rule part 1. The goal is to compute the indefinite integral of f of x. This theorem says that we can integrate in terms of u first, and then substitute h of x back into u. In the condition, u can be an arbitrary function, as long as f of x times the reciprocal of the derivative is a function of u. However, we usually use this method with u being part of the expression of f of x. For example, suppose f of x is complicated, but with u substitution, f of x times the reciprocal of the derivative may become a relatively simpler function of u, so that the integral in terms of u is doable. Then, the theorem suggests that we will be able to reach the solution via computing the integral on the right-hand side of the equation. Here is a good example. Usually u is part of f of x, and if u is 1 plus x squared, it turns out that g of u is fairly simple to integrate. In fact, it may take multiple practices to be good at picking u, and here we shall just focus on how the rest of the mechanics go. Du dx is 2x, and as we take the reciprocal, it cancels with one factor, making the u integral easier. If we directly apply the theorem, the dx integral switches to the du integral as shown in the middle of the video. The bracket is a reminder that we should integrate with respect to u first. Probably you can compute an antiderivative of 1 over 2 times u to the 9th. Please take 15 seconds to do an exercise of computing this antiderivative in u. One over 20 times u to the 10th is an antiderivative. The last bit is to simply substitute 1 plus x squared back into u. As mentioned earlier, it takes multiple practices to be able to make a good choice of u. But a general principle can be as follows. The first goal is to choose u, such that a functional multiple factor is cancelled as we multiply the reciprocal of du dx. For this example, such cancellation does not seem to be available. Then the second approach can be to choose u to be a linear function. As shown here, no functional factors are cancelled out, but the 9th power becomes a monomial in u, which is easy for integration. Remember that we need to write the function all in terms of u, before we actually integrate. So the factor of x there must be rewritten in terms of u. The reason we looked for a linear factor is explained at this stage. Namely, we can write that x in terms of u neatly. Now we replace that x with this u minus 1 over 2. Altogether there are 2 copies of 2's in the denominators, so we have 1/4 as a constant multiple. Now we reached an expression with which integrating is fairly easy. Using this method efficiently takes practices and time, but surprisingly understanding why the theorem is true is quite easy. Let us explain that now. First we shall simply prove the conclusion, and later explain a bit more about how they might have discovered a statement like this. Since the left-hand side is solely an indefinite integral, it is sufficient to prove that the derivatives of both sides are equal to each other. The derivative of the left-hand side is f of x, since the indefinite integral represent antiderivatives, and their derivatives will be f of x by definition of antiderivatives. The derivative of the right-hand side looks like this, and the key observation is that the expression is all written in terms of u. You may have noticed that this is exactly the situation for using the chain rule. So the whole expression is treated as a function of u, and differentiated with respect to u first. Then we multiply du dx. This is the chain rule. By definition of antiderivatives, the du part is simply g of u. Since g of u is f of x times the reciprocal of du dx, the two factors cancel out, and leave f of x alone. Therefore, we prove that the derivatives of both sides are equal to each other. Let us now think backward a little bit, and explain how one might discover a theorem like that. It is reasonable to see that developing integration techniques must begin with reversing derivative rules. If we consider the chain rule, we use u substitution to differentiate with respect to u. So we may formulate an integral version that corresponds to the chain rule as follows. We want to compute the indefinite integral of f of x, and we want to do some sort of substitution first, and integrate with respect to that variable later, and eventually reach the same answer as we substitute it back. What could that substitution be? Its mathematical version is shown here. To get to g, we shall differentiate both sides. And we have to apply the chain rule for the right-hand side. Then, as explained earlier, we have this extra du dx as a result of chain rule. We want to know what this function g of u is. So if we solve for g of u, we discover the condition that appeared in our formulation of the substitution method as a theorem. Thanks for watching, and in the next video, we shall introduce the second part of the substitution method.